Okay, so for whatever reason, the part about coherence didn't get saved or didn't get uploaded or whatever. So I'm gonna try that again. Okay, let me see. Let's start again with the left mid bass. So that's where we're at now. So let's get these guys off of there. I've already set reference delays and all that stuff, so we can take a look at the average. So this blue guy here, that's the average, and then all of these, in fact, let's go like this. So yeah, so the blue is the average, and then of course all these multicolored things in the background there, that's the each contributing microphone. So let's take all the individual mics away and just take a look at the average. Now, with coherence and the coherence blanking function, what we can do is we can use Smart's multi-time window to help us determine at what frequencies directionality starts to play a part. So, you know, obviously with the like 6.5-inch diameter speaker, kind of door mounted, depending upon how it's mounted and where it's mounted in the doors, because door mounted could mean a few different things. In this particular car, it was a Kia, I think, or Hyundai, one of those, and it was kind of mounted high in the door and even maybe aimed very slightly toward the listeners, I think, if I remember right. Either way, it was high in the door. But anyway, so, you know, as we're measuring and listening to these things considerably off axis, especially for the left one, maybe a little bit more on axis for the right one, you know, there's the frequencies at which the speaker starts to become more and more directional is going to play a part in our crossover selection, our crossover choices. So normally, if you're measuring these types of things with a kind of a conventional, you know, REW style way, you might be seeing traces something like this, right? This would be an average, you know, and the contributing traces to those averages would be like this red one, like this probably looks familiar, right? Like that's kind of what you're used to seeing, you know, FFT measurements, you know, you got all this real high frequency kind of noise looking stuff at the top end due to the excessive number of data points and all that kind of thing. So, you know, but then whenever you do an average, you know, it definitely smooths out considerably. Let me let's make that front trace not quite so thick there. So it definitely smooths out considerably compared to the contributing microphones, but still, you know, there's still quite a lot of kind of noise on that top end. Now, let's just take a look at mic number 4, our middle microphone, and compare it to our average. So that's using a standard like 32K FFT, right? Now, if we switch over to Smart's multi-time window, this is now the results that we get. So we have a more of a consistent number of data points throughout the logarithmic displayed spectrum here, and our resulting traces are, you know, they're not so overcome with just excessive data on the top end. You know, there's still a significant amount of, you know, but it's not so overwhelming like it is with the single size FFT. And then somebody might say, well, who cares? With the single size FFT, all we have to do, like right here, 32K, right? All we have to do is come in here and put some smoothing and problem solved, right? Well, that is true, problem solved, if that's all we were caring about, but it isn't. There's another key to this whole process, and that is the coherence and the coherence blanking feature. So back to the whole directionality thing. Of the speakers beginning to kind of beam as frequency increases. With the coherence blanking feature, there's and well, with dual FFT in general, you have this new thing called coherence, which is right here in red at the top. All right. So what coherence shows is it shows the signal to noise ratio, if you will. If you define signal as being direct arrival energy. So in other words, signal would be like, let's see here. This would be signal here in the beginning, whatever we put at our reference delay, whatever our time 0 is, right? Which we would want that to be the arrival energy from our speaker, the direct arrival energy. All of this later stuff here that is not in the anechoic response of the speaker, these later reflections, these are quote unquote noise, right? Signal to noise ratio. So that's kind of the easiest way to explain how coherence is going to be affected in the car. There's other things like, other sounds, ambient noise, going on that's going to, drop the coherence. But when we're in a sealed car, the coherence trace is pretty much reflecting nothing but the actual acoustic, phenomenon occurring within the vehicle as a result of the speakers. And it's really not, in other scenarios, like you might read a lot when you read about these programs, you might read about coherence being kind of a measure of measurement quality or trustworthiness of the data. And this can absolutely be the case when you're, measuring outdoors, when you're measuring indoors in a large venue, when you've got other noises going on, when you've got, all kinds of other things. So the coherence trace can be a reflection of many things. But when you're in a sealed car and you have excellent signal to noise ratio anyway, then the coherence trace really becomes an indicator of the directionality of the sound that's coming to the microphone. Is that sound coming to the microphone directly from the speaker, or is it arriving later as a result of reflected energy? And does that reflected energy that's arriving later, is it greater in quantity than in that frequency range? Is it greater in quantity late arriving than direct arriving? So that's, I hope I explained that well. I don't know really how to word it that well, but anyway, so if we switch, okay, let's take a look at the coherence trace again here. All right, so with multi-time window, we can see that our coherence really starts to kind of break up down here around 2K, right? With this particular speaker in its particular orientation. Let's switch over to a conventional 32K FFT. So 32K FFT, our coherence stays real solid, much higher, right? And that just has to do with the fact that the time constants in question are much longer up here in these high frequencies. Well, it's one big time constant. So the 32K FFT, that time constant applies to this entire acquisition. With the multi-time window, we have a bunch of different time constants, and the time constants get shorter and shorter and shorter as frequency raises. So coherence now becomes a very useful measure of direct to reverberant ratio. So when we're on multi-time window, we can now use the coherence blanking feature like this, right? To start, we take our little handle right here and slide it up, and it starts to blank out the regions of the response that have a poor direct to reverberant ratio, where the reverberant is starting to overwhelm the direct, right? And so that would be what's called beaming, right? In kind of car audio terminology, and you hear that a lot. And anyway, so you hear that term, beaming. So yeah. So anyway. So that's how coherence can be used in the vehicle after the installation is done to start being able to measure at what frequencies does the speaker start to beam compared to other frequencies, from that microphone position, or in this case, from that average microphone array, right? So what we would do is we could say, well, we have other, known factors that are going to help us determine our crossover frequency, like, for example, the tweeter's impedance trace, right? We take an impedance trace of the tweeter and measure its FS, and we say, okay, well, we don't want to excite the tweeter at FS. Generally, we want to stay above that, So that kind of helps us define a kind of a maximum lower limit, and then with that defined, we can say, okay, so we know we can't go below this certain point with the tweeter. In fact, let's switch over to the tweeter. Let's save this guy. This is left mid bass. Okay, and now let's switch over to the left tweeter. And now we're going to switch our tabs to tweeter left. and hit play, and get those guys out of the equation. Everything but the average. Okay. And we can take a look at our left mid bass again. All right, so here's our left mid bass as compared to a live trace of our left tweeter. Okay, so now when we slide our coherence blanking up, we can see, okay, so the mid bass starts to blank out, right? It starts to blank out at these frequencies. So we know, like, you know, of course, this crossover filters were already set on these speakers when I made this recording, but still, we could say, you know, if they weren't set, we'd still see this same effect occurring, you know, through here. So the mid bass would be carrying on up like this, and our tweeter is going to start kind of blanking out, you know, down here in frequency. So we know where our tweeter starts to blank out, our mid bass is still good. Where our mid bass starts to blank out, our tweeter is still good. So, you know, that helps us determine where can we place our crossover, because we want we don't want to place our crossover where this speaker is, you know, beaming heavily. You know what I mean? It's much better if we have good solid coherence throughout the entire frequency band once everything is playing all at once. I feel like I'm not doing a good job of explaining this morning. I think I did a better job yesterday. But anyway, so that's, you know, more or less that's kind of the concept behind coherence blanking, and how multi-time window in Smart can be very useful. You can, in fact, you can turn the coherence trace off if you'd like, and just use just the blanking function. I personally prefer to leave coherence on. I don't know. I'm just used to seeing it, and it's also an indicator of, you know, other things like measurement issues, noise in the signal chain somewhere. If, you know, if there's something going on and you're not getting good data and you're not 100% sure why that is, the coherence can be an excellent indicator of that. In fact, if you switch over to 32K. You can see now, since these tweeters in this vehicle were mounted largely on axis, you can see at 32K your coherence is just completely solid all the way out, right? Because the time constant is much longer, so the direct to what's defined as reverberant ratio is much closer to a you know, like a 10 to 1, you know, in favor of the direct, with that kind of a time constant. But anyway, so yeah, so with big single size FFTs, you can use the coherence now to make determinations about, you know, to kind of as a sanity check to say, well, am I getting good signal? So, you know, it still can be used as a kind of a verification method or signal measurement integrity kind of a thing. But yeah, so once you've established that, yep, everything's good, I'm getting good solid coherence, you know, on each one of my individual drive units, then you can switch over to multi-time window like this, and now you can actually use the multi-time window derived coherence as a means of aiding the tuning process. So yeah, I guess that's it for now. I feel like I did a better job explaining it last time, but oh well.